So welcome everybody to this seminar, who is the last seminar of the second part of this cycle devoted to COVID and complexity. So we are very pleased to have you around, and of course we are very pleased to have our speaker today. And okay, just to welcome everybody, and I will give the word to Álvaro Corral, who will introduce the speaker and who will be the chairman of the session. Álvaro, please.
Thank you very much, Albert. Just maybe some of you don't know this platform. At the end, we will have a question for Lucas. So there is a chat. You can write that you want to make a question in the chat, and also you can try to raise your hand. Just look to the buttons of this platform, and let's start with Lucas. It's a really pleasure to have here Lucas Lacasa. Lucas Lacasa is a physicist, and he got his PhD in the Universitat Politécnica de Madrid. And then, well, he went back and forth as usual in this discipline. Even he was a part of the Catalan member of complex systems a long time ago for a short period, and then he moved to US, and then he got a permanent position in England. Also he got a early career fellowship from the EPSRC, and now he's a reader in applied mathematics at Queen Mary University of London. Thank you very much, Lucas. It's a pleasure that you are here, and we are very interested in your talk.
Thanks very much, Alvaro and Albert, and for inviting me today. I'm going to present this study, which has been done in collaboration with a few people. So it's been in collaboration with Robert Challen, who is a medical doctor in Exeter, and Ellen Brooks Pollock and Leon Dannon, who are mathematical epidemiologists in Bristol University. Actually, Leon is well known to many of you and actually says hi. So this is about reducing the stress on intensive care by optimally or quasi-optimally load balancing patients. So let's dive in. So the motivation for this work is actually quite straightforward, I would say. During COVID, in the last 10 or so months, we have had several outbreaks. And whenever we have an outbreak across the globe, hospitals in that region can get overwhelmed very fast. Basically because even if at the individual level, the lethality of the virus is not very big, it spreads super fast, so that has a very damaging effect. So whenever a hospital is overwhelmed, this leads to a cascade of deaths due to the collapse of the health system. It's just not just that COVID patients cannot receive the proper care anymore, but actually any kind of patient won't be able to receive proper care. So if you are involved in an accident, or you have a heart attack or something like that, and intensive care is collapsed, then you're likely to die. So I don't have to convince you about this fact about hospitals getting overwhelmed. We have seen this over the news in the last months across the globe, both in the UK and also in Spain. And actually, right now, for instance, in London, where I work, the situation is very, very complicated, and it is expected that actually hospitals will be overwhelmed in a few days. One can see this, for instance, if we look at admission curves. So this is admissions to ICU, so intensive care. Over time, the gray line is in England, and the blue line is in London. So as you can see here, we are here. Well, you don't see my mouse. Sorry. We are now right here, and we are already in levels of the peak that happened in April. During that peak, some of the hospitals in London were overwhelmed, but then we had the Nightingale. It is expected that this curve will still grow up, or increase. So in a few days, it's not going to look nice at all. So the good news, if we can say that, is that demand is usually heterogeneous, so the demand of anti-intensive care, I mean. So collapse does not happen everywhere at the same time, okay? They are like the incidence curves increase and decrease in an asynchronous way. One can see this, for instance, here I'm showing you the a plot of the cumulated incidence per week across the UK, and one can see that different regions have different incidences, right? Actually, the same happens, for instance, at the regional level, not only at the level of the whole country, but also regionally. Here I'm showing you, again, cumulated incidence, so that per week. So this is not per 14 days. This is the standard in Spain. It's per week. So to compare with Spanish rates, you have to multiply these numbers by 2. So the color code here is that towards yellow you have higher incidence, towards dark blue you have lower incidences. And although, so here I'm showing the different neighborhoods of London, and that's over time. And now, well, this is basically the effect of the new variant, which is quite scary. But as you can see, different neighborhoods are, let's say, all of them have very, very high incidences, but still this is not homogeneous, right? So that means that hospitals for instance, in Barking or Newham, etc., will be overwhelmed faster than some others in some other areas. Right. So this basically allows us to transfer patients, right? Which is the reason of this work. This is an idea that has already been contemplated by several countries. So here, in this example, I'm showing this is a rather bold transfer method where France considers transferring patients to Germany, which is, I would say, inter-country transfer, which is a little bit radical. But then at the more regional level, in Madrid, actually during the first wave, some medical doctors from different hospitals self-organized between themselves to be able to transfer patients between the hospitals, in a spontaneous way. There have been also attempts in the US, etc. Now, transfer patients is, I would say, is rather obvious, but the thing is, when you have we have more than a bunch of hospitals to transfer across, then we have to be very careful, because transferring, in a random way could do more harm than good. And to give a very simple example of what I mean, I'm plotting this very, very basic toy model. So we have here 5 hospitals, 1, 2, 3, 4, 5, and I'm plotting here the local stress, which basically means the number of patients that or the number of beds in excess that are required. So for instance, in this case, hospital number 2 is overwhelmed, and actually it needs to allocate 8 more beds or 8 more patients than its capacity, right? So well, I would say a natural solution for this would be, okay, I look around and I see that I have 2 neighbors, which is this one and this one, which are okay. I'll take the hospital with larger capacity, which is this one. It has 10 beds available, and I'll transfer some of my loads there. However, if you do that, then this hospital is also overwhelmed, and the only possibility of transferring is also here, and that results that maybe we cannot transfer anymore, because hospital number 2 already transferred some, right? If hospital number 2 instead had transferred to hospital number 1, then hospital 4 could have transferred as well to number 3. So you see, this is a very stupid example where you can see that if you only consider what's best for you, that in the case of hospital number 2 was transferring to 3, then you end up doing more harm than good. Concretely here, we would be collapsing number 3, or even not allowing number 4 to transfer. Right. So so with that in mind, here I'm showing you basically the goal or the wish list that we had. So we started to work on this project in mid-March of last year. And so it was at the beginning of the first wave. And so basically we wanted to set up, first of all, quickly, a simple and flexible load balancing model, okay, which could be used at different levels, right? So at the countrywide level or also regionally. We also wanted the model to find quasi-optimal configurations, so basically avoid the situation that I just explained or other similar situations. Try to find a way of allocating patients between hospitals such that globally the number of patients that could be allocated was maximal, right? I have to emphasize, we wanted to define this kind of load balancing model without the needs of increasing the capacity of hospitals, which were already increased due to surge capacity. So we just tried to find the spots. Originally, the idea was to distribute critical care patients or patients needing critical care. But of course, the method I'm going to show you is much more general and applicable to other circumstances. No? For instance, now we're currently considering care homes, which is another setting. Now, I have to emphasize that our idea was to develop a quick and easily operationable optimization method rather than some sophisticated mathematical approach. So our goal was not to produce a paper, but to produce something that could be useful in the context of COVID. So this is more or less the roadmap. We started working on mid-March, then we were able to produce a preprint by the end of March to be discussed at SPIEM. I forgot to say that both Ellen and Leon, two of the co-authors, sit in the SPIEM committee, which is one of the committees that gives advice to SAGE in the UK. And then we had a prototype or a proof of concept to be applicable by the NHS, ready by early April. Spoiler: we didn't need to use it because of here what we call Nightingale hospitals, which are large field hospitals which are built up ex professo to deal with the pandemic. You know, it's, for instance, the IFEMA hospital in Madrid. Probably Nightingale hospitals won't be enough in the January wave in London. Then we were able to discuss at some point with the government of Comunidad de Madrid by mid-April. It was funny because they were interested, but then they were not interested. They stopped answering to emails. Not sure why, but that's what happened. And then we got a grant from EPSRC to start operationalizing. Oh, wow, this is a very difficult word. Operationalizing the method in June, and that was done or is being developed now in collaboration with Raw Data, which is a UK company that is a data science company that is a specialist in epidemiological data. And the paper I'm presenting today, or part of it, was published in October. So that's more or less the summary. So let's dive in. So what did we do? As I said, it's a load balancing algorithm. It's very close to what you would imagine, I would say. It's nothing fancy from a mathematical point of view. So it's a local load sharing algorithm embedded in an hospital transfer network, okay? Let's look at the figure to explain a little bit what happens with the algorithm. Consider that, well, first of all, we have to define a hospital transfer network, and I'll do that in a moment. Okay, I'll show you what kind of hospital networks we have considered in this work. But once you have defined that, suppose that you are here. You are in a hospital or in a region where you think you will be overwhelmed soon, or you are already overwhelmed. That's why the red color. So you need to load to transfer some patients. Okay, why does that happen? Because maybe the demand that you project for the near future, or the demand you have already, is larger than your baseline capacity. Okay, that means that this quantity, what we call local stress, is positive. Okay, if that happens, what you do is you look at your neighborhood, and you look all the hospitals which can be, let's say, have green light. So all the hospitals that have negative local stress, right? And then, well, then basically you choose one of them and you transfer some loads. Okay, you can do that in a variety of ways. You can do a sequential update or a parallel update, which are, I would say, technical details which are not really important at this point. Then to evaluate, so you do this for all the nodes, right? And then you have to evaluate how good you did. Of course, you only balance loads or patients to those hospitals that can receive patients and so on. So to compute how good is, the performance of your solution, you define this global stress function, which basically sums up all the positive local stress only. So basically, this global stress only means you sum all the patients that cannot receive any care. Okay, and the idea is that you want to minimize this global stress. That's our cost function. And what we do is here we have adopted a very simple random search optimization. So basically, we run a lot of different stochastic realizations, where in each case we select at random hospital to allocate or the patients, and then we just choose the realization, the configuration that minimizes the global stress. All right, so what kind of transfer networks do we have? Here in this work, we have worked with UK and Spanish data. So we have defined essentially, well, I would say 2 or 3 types of networks. In all of them, well, the nodes, sorry, take the pen again. You're seeing the pen, by the way, right? I hope you're seeing, because I'm using it.
I'm not seeing now, Lucas.
You're not seeing any pen? What I'm using? I mean, not
no,
now, but
no.
Yeah. When you write, we can see it. We can see it.
Okay.
Yeah.
Okay, thanks. All right, so nodes are hospitals, but not just hospitals. Actually, for instance, in the UK, as I'm gonna show in a minute, the UK is distributed in what we call trusts, which are conglomerates of hospitals. So nodes can be hospitals or conglomerate of hospitals, or actually even regions. Edges define transfer feasibility. So 2 nodes are connected if one can make a transfer between these hospitals. For instance, the network can be weighted if you want by putting here a number which can be related to the distance, for instance, of between the 2 hospitals, or by some other quantity. So for the UK network, this is a tessellation, as I'll show you in a minute, but this doesn't have to be the case. I have to say also that nodes are this is a spatial network, so nodes are geopositioned And in the general case where a node is defines a conglomerate of hospitals, you just do what you expect, right? If a node defines a conglomerate of M hospitals, the position of this node is just the barycenter of the geographical coordinates of each of the hospitals. Okay. So more concretely, we are dealing with UK data and Spanish data, as I said. So let's start with UK data. We have what we call trusts, right? So as I said before, a trust is a conglomerate of hospitals, which have a fairly independent management. So all of the hospitals within a given trust are managed in common. So it makes sense if you want to load. So yeah, I forgot to say, in a given trust, not all the hospitals will have ICU. So we have intensive care units, of course, maybe some of them. So it makes sense to transfer loads between trusts. So in the UK, we have 141 trusts, which are the red dots here in this image. And then we build a 4 regular geometric graph. So we tessellate the space more or less to build this geometric graph, such that we select. So basically, for each trust, we select the 4 nearest neighbors in the physical sense. So we use physical distance to select the 4 closest neighbors, and we link them. All right. So that's the transfer network in the UK. Then we also worked with Spanish data. And this is an interesting case because in Spain, as you know, the health system is decentralized as opposed to the UK. So it doesn't really make sense to transfer patients between hospitals across the country. That only makes sense to do that within a certain autonomous community. However, as we already do that in the UK, here what we did was to study inter-community transfer. So here what we define is a network of 17 nodes. Each autonomous community is a node. We discard the islands, so the Balearic Islands and the Canary Islands, which is more or less somewhere here, for obvious reasons. So load balancing will be complicated there. So we have 15 nodes then, and we define or we study two types of networks. The first network is a contact network. Okay, so basically any 2 nodes are connected by a link if the autonomous community share a border. So for instance, here this is Galicia, and this is Asturias, and they share a border, therefore they are 2 connected nodes, okay? By doing that, what we have is a network which is heterogeneous, right? So in this case, we have the degree varies between 2 and 9, which is the largest degree. This models the situation where a given community will transfer that by ambulance, not to its closest autonomous community. A second possibility is to build up a fully connected network, assuming that within the mainline Spain, any community can transfer patients to any other community. For instance, using the train network. And this is a situation that actually was considered initially. I remember back in April, Renfe was already preparing trains with necessary equipment to transfer critical patients. I don't know if you remember. All right, so let's go into the results straight away. And so we have defined, I have basically told what the algorithm does. I have defined the networks. Let's see the results now. We start with the UK. So I'm showing you now 4 panels. The panel on top, to the left, I'm plotting the histogram of the capacity of each of the trusts. So most of the trusts I have, let's say, moderate to small ICU capacity. I remember ICU is intensive care unit, okay? So it's basically critical care. There are just a few number of hospitals which have larger amount of beds, so of, with ventilators and so on. So now here in the right hand side, I'm showing you an example of what happens before the algorithm and after the algorithm. Okay, so I'm plotting the histogram of what is the local stress across the UK. So I'm looking at all the trusts. I have a capacity, okay, which is defined, the number of ICU beds available, and I put a synthetic demand, okay, such that some of the hospitals are overwhelmed, okay, and then I look indeed how many of them are overwhelmed. So anything above 0, so larger than 0, is overwhelmed. So all this area means overwhelmed hospitals. And then I apply the load sharing method, and then I add the red, the green curve. So as you can see, many of the above 0 goes to 0, which means that they were able to share the loads. So that's good. Then we go back to, we go to the figure on the bottom left. Here I'm plotting the global stress, which is this cost function that we want to minimize, as the total number of beds above capacity, so the total number of patients that cannot get any care because of this system being overwhelmed, as a function of the demand I put synthetically. No, I'm tuning my system for more and more and more and more and more demand as I go towards the right. And the red line is the system without any kind of load sharing. So as you can see, as the demand increases, the hospitals get overwhelmed, and therefore the global stress increases. That's rather obvious. And once I switch on the load method, the load balancing method, just single algorithm step already alleviates, in the sense that it pushes towards the right this curve. So to be able to quantify how much alleviation, what we do is basically count what we call the net reduction, which is basically the number of ICU beds that we weren't able to provide critical care before the load sharing, and now after the load sharing we found spots, and therefore we were able to give them a bed. So again, as a function of the uniform demand, so the demand per trust, which increases uniformly, what we found is this sort of non-monotonic behavior. It's not important. I mean, don't focus on the different points, because they are just technical details of different ways of implementing the algorithm. But basically, here it's important to see that we have sort of three regimes, right? The first regime, where basically here the demand is small, okay? Only very few hospitals are overwhelmed, and therefore the load balancing method is switched on only occasionally. Accordingly, the reduction is the number of patients that could be load balanced is rather small. Then there's a second regime, which we could say the optimal regime, where we have now several hospitals which are overwhelmed, or several trusts which are overwhelmed, but still the system is able to load share. And we can reach high levels of sharing, up to 1,000 beds in a single step of the algorithm. And then when we increase even further the demand of the whole system, we reach a third level, where a third regime, where now everything is pretty much collapsed. Everything, there's no space to share anything else, and therefore, in that case, the net reduction drops. So these are the results for, I would say, a synthetic analysis. It's important to say that that the runtime is rather quick. So we only need a few seconds of, I mean, the runtime is just a few seconds, and we're finding maybe not rigorously the optimal solution, but probably a very good one. So this is encouraging, thinking about operationalizing this method. Okay, technical detail. Here I'm doing a single share. That means that the algorithm, whenever you have a node and you, which is overwhelmed, and you look around to its neighborhood and you find a neighbor, you only are allowed to share once. You're not allowed to share several times with different neighbors. Okay, that's just a specification of the algorithm. So you can change that and do instead what we call multiple share, which is again just another technical difference of technical specification of the algorithm. And we can compare single share versus multiple share. And basically, the result is that the efficacy of the method is enhanced with multiple sharing, as you would expect. Okay. So it's nothing important about this slide. Okay, so let's move to a bit more realistic analysis. So here I'm showing you. So this is the UK. Probably you could imagine the shape. That's basically UK for a physicist. So the points are the trusts, the UK trust, the 141 trust. The size of the point characterizes the capacity of the trust initially, the number of beds available initially, assuming that all the beds will be for COVID, by the way. Then the color of each point describes how the demand or the local stress, better put, by 1st of April. And these are real data. So anything in green or yellow is a local stress which is negative, and that means that they are okay. They have beds in excess. Anything which goes darker, like more red, means overwhelmed. Okay, the local stress is positive, so they would need to balance. They have patients that they cannot treat. So that's before the load sharing. So before LS means before applying the method. And then if we apply the method, what we find is this. Just a single step of the algorithm improves a lot. You know, this is basically the regions in the southeast. This is London and the neighborhoods of London. This is yeah, here we have also another problem which is not solved, but essentially everything is much better at the load sharing. Here I'm showing you the same thing, but now with real data on the 4th of April, where things got even worse. And as you can see, it after the load sharing, everything improves. Everything goes, almost everything goes towards greener colors, I would say. So not overwhelmed. This is an emphasis. So a zoom near London. So you have to trust me on that. This is near London. So I'm zooming here, and as you can see, they have a lot of trusts, and many of them are overwhelmed according to this color code. And then we apply the load sharing, and what we have is everything is reduced substantially. So basically, here the message is that in a situation with, you know, in this regime number 2 that I said before, when you have several collapsed hospital or overwhelmed hospitals, but not everything is collapsed, then the method is able to find these spots, right? I just remember, I want to remind that here I'm using the 4 regular graphs. So each bubble here, or each bubble here is a node. And what I'm doing is to find, the 4 closest, maybe this one is here, the 4 closest nodes and connect them, okay? So I am only allowed to transfer to the 4 closest ones. All right, so that's for London. Let's move now to results in Spain. So this is basically a summary of what we have. So this is Spain. Well, yeah. Before load sharing, the color code here is a little bit different. I'm showing here. This is again the local stress. So everything reddish is larger than 0, means overwhelmed. Everything greenish is the autonomous community is doing fine, is below capacity. I don't remember, I think this is based on, oh yes. So this is based on the demand versus the capacity, according to what we call, so not surge capacity, okay? So to compute this local stress, in this case, what I'm using is the number of available intensive care beds before the pandemics, okay? So I'm not counting all these intensive care beds that are available because hospitals are not doing any surgery anymore. So we are using surgeries to put there, people, because they have ventilators and so on. So according to that, before load sharing, this was mid-April, I think, when we did this analysis. So the center of Spain and Catalonia, and it was very, very bad. And then applying the local load sharing, so using the contact network, so the first network I defined for Spain. So when being able to transfer only between adjacent communities, it alleviates a little bit. Some communities like Catalonia or Madrid are still overwhelmed. But then if you do, well, actually they're all the time overwhelmed. If you do the countrywide sharing, which is using this fully connected network, everything improves substantially. Here on the bottom, I'm showing again the global stress and the net reduction. And here the x-axis is it's a little bit different than before. So I have data, say, for when the system was had a global saturation of about 62% or something like that. Okay, so that's real data, and then I analyze what would happen if I increase proportionally. So each autonomous community has a surge which is proportional to the amount of demand it has at this specific point. What would happen with the global stress? And the black line is without any load sharing. So once you start to have things overwhelming, it increase more or less linearly. And then after load sharing, either with a contact network or the fully connected network, what you have is that the curves push towards the right. And here I'm showing in the right hand side, I'm showing the net reduction. So the number of people that didn't receive or couldn't receive care, that after the load sharing can now get a bed and a ventilator. As you can see now again, we find, at least for the fully connected network, we find this sort of non-monotonic behavior. So when the system is in a, so when the saturation is not very high, then not much is load shared, so we don't have reduction. When the saturation is super big, everything is overwhelmed, so we cannot really share much, because not any hospital will or any community will want to receive patients. But then in the middle we have actually an optimal, which can go up to 1,300 patients per algorithm step. I would say about 50% of these could save their life. Okay, so that's, in terms of results, that's pretty much it. So let me just say a few words to wrap up. So we wanted to build a simple and flexible load balancing model, which could be used at different levels. So here I have shown you results for the UK at the countrywide level, but also at the level of just London. And then I show you also at the countrywide level in Spain. We could, of course, implement this within a specific autonomous community. We didn't do that at the time because we didn't have the data, just the data about the geographical position of the hospitals, etc. The model needed to find what we say quasi-optimal configurations globally. So again, we don't have a mathematical guarantee that the configuration we select among the 100,000 we run is the optimal one. We only know that it's a local optimum, but according to the results we find, we are confident that it's a very good solution. It's in principle designed to distribute intensive care patients, but of course, if you think about it, it's very general. You can distribute anything you want, actually, like ventilators as well, or implement in other settings. For instance, now we are considering, as I said at the beginning, we are considering implementing the model in care homes to be able to optimally allocate people in different care homes. By applying the load sharing algorithm, one can redistribute or up to 1,000 patients per iteration, which would potentially mean saving 50% of these lives, right? Because we know that about 40 or 50% of the people that are in intensive care die, but the others are saved. But if you don't get a ventilator, then you don't have that possibility to save your life. So the model is minimal, of course. This is a very simplistic. We needed it, to be simple and dirty. Now we can add as much complexity as needed. Okay, we can implement different cost functions on top of it. We can implement different search algorithms, something like more fancy than a random search optimization. We can do many things. Okay, so the model is basically a skeleton over which we can now improve a lot. So that's, let's say, from a scientific point of view, we have still many things to do. But the real challenge here is this model was initially conceptualized to not be something very fancy, but be something that could help. And in the sense, the real challenge is indeed to be able to integrate this kind of approaches within a regional or a national strategy. Okay, so implement it, for instance, in the NHS or in the Spanish health system. And as it turns out, in my experience over these last 10 months trying to work this out, this is more of a political challenge than a scientific challenge. So I've learned that you cannot really just give them an algorithm and some results to a government. They won't do anything with that. You need to be more pedagogical and propose something which like a full service, maybe, so that they can use it. And in this sense, that's the reason why now we are in the process of trying to operationalize this idea. So we are developing this as I said at the beginning, in collaboration with Raw Data, which is this company in the UK which deals with these sort of things. Maybe I could. Let me check. So I'm gonna stop sharing for 1 minute, because I want to. Well, maybe in the questions. So we have this is just a snapshot, but we have this kind of dashboard where you can select the hospitals, and the idea is that basically we need to provide this kind of end-to-end interface to the people that take the decisions. Otherwise, they won't really use it. That's basically the lesson we got. And so that's what we're doing now, trying to build a front end for the health system to use it, and also working on some improvements on app. For instance, we are working on level propagation algorithm to dynamically estimate the catchment areas of the different hospitals. But anyway, that's basically everything I wanted to tell you. So let me finish by thanking you, everybody. So this is the paper we were able to publish, as I said, with Robert, Ellen, and Leon, who are my co-authors, and these are the people that actually know something about COVID, because they are actually professionals about it. That's pretty much it. Thanks very much. So now, if you have any questions, I'll be very happy to tell you to answer them. Thanks.
Thank you very much, Lucas. Very nice and very clear and very interesting. So if some of you have questions, on the right of your screen, you will see a chat, and you can write your name or whatever. Roger Guimera, I see. So Roger Guimera knows how it works. So Roger Guimera, the micro and ask.
So I have a couple of questions. One is regarding the global optimality, and you mentioned this in the conclusion, so I was about not to ask the question, but I thought I'd ask it anyway, about the global optimality of the solutions that you get with your method, right? Mm-hmm. So it seems to me that there might be a sort of a mathematical programming approach, like a linear programming, or I don't know, mixed integer linear programming perhaps, or I don't know, mm-hmm. something like this, that might allow you to get an optimal solution. Yes. Of course, it's not my expertise, so I'm not sure that this can be done, but it seems like the kind of problem that you could typically address with this method. So, well, that was my question. Do you think it's possible, or have you considered this, or so this is like my first question. I have a second one too. Maybe I can ask him. So the second is, what about times, right? So you have this load balancing. So you move some people from one hospital to the other, but even with the experiments that you do with real data, what happens if you put time in there? So you take the next snapshot, and now you have to move, like, let's say you have to move people from Catalonia to Aragon, right? Because Catalonia is overwhelmed. And then after a while, Aragon is doing pretty poorly as well, right? So then you have to move people from Aragon to whatever, La Rioja, and you keep moving people all. So I would be interested in knowing if you've considered this effect of time, and if you can quantify whether in the end, I mean, I'm sure that you'll still be able to put more people on ICUs, which is good, but you also pay a price on moving people around, which might have problems in terms of contagion and economic and others, right? So I wonder if you've considered this.
Yes, well, thank you very much, Roger. The questions are very good.
Talk, by the way. Sorry.
Thanks, mate. The questions are very good. We have considered, but we haven't done anything about it. We know that, for instance, you pay a price to put someone with COVID in an ambulance and bring it to somewhere else. First of all, because you are taking someone who is contagious and doing that, and also because of all the other things you said, right? In principle, all these considerations can be added to the algorithm. For instance, when you put a weight between the two nodes, you can put something like, so in terms the distance between the regions is a proxy for how much time it takes to move to Catalonia from Catalonia to Aragon, no? But then also you can put a weight in terms of how many ambulances are there, basically how much feasible it is. So we haven't done that in our approach. It's as I said, it's minimal. Our approach is minimal. I would say that ideally, for instance, in Catalonia, if people from the government take this and try to do this regionally, then it would be a discussion between the policymakers and the technicians that run the algorithms to decide what kind of specificities you put into the model. You know, what kind of weights you put into the links according to the priorities that they might have, which could be clinical or could be economical, as you said, or etc. And then the other thing, you're totally right. Probably you can phrase this in a like a linear integer programming. Not I don't know if linear, but definitely integer programming problem, and maybe you can find the optimum. We just didn't take the mathematical approach very seriously. We only wanted to do something that more or less works. Thank you.
Okay. Thank you. Now we have a question from Montse Guillén. Montse Guillén, you can open the microphone. Montse Guillén is a professor of economics at the University of Barcelona. So go ahead, Montse, if you can, if you have a microphone.
Yes. Hello, Lucas. I think this was an excellent talk. I loved it. But we have also analyzed this kind of data. That's the reason why several people from my group have joined the session today. And we wanted to ask you about the heterogeneity in patients as well. I mean, when talking to doctors, we think that some of the patients sometimes cannot really be moved from the place they are, or are so severely, taken by COVID that they really don't think about changing them from short distance hospitals. And so did you have this fact as a constraint or a possible constraint on your model, or something like that? Thanks for the talk. Thank you. Thank you.
Thank you very much. Thank you. The sound was not very great, but I think I understood. You were asking about what happens if the patient is so severely ill that he cannot be moved and so on, right? So we consider that possibility, of course, but again, this is, I would say it's more like a toy model than a realistic model. When we discussed about that, we thought that this approach can be used not necessarily, to move patients which are already in needing an ICU, but you can plan it in advance. So if you are able to estimate the demand of ICU that you will have next week, for instance, and that we know that you can do according to several approaches, according, for instance, to the amount of hospital admissions that you have this week, then you can start to plan. And as soon as so you plan, for instance, okay, I have a plan that these patients, or the next 5 patients that require moving will go to this hospital. And as soon as patients start to look like they need ventilation, then you don't wait until they are so ill that you can move. But again, this is something which I'm not an expert here to comment on. So probably some like intensive care doctor could say that I'm totally wrong here, and they could not move. Thank you.
Thank you. We have a question by Albert. Albert, please go ahead.
Okay, wait. I think we have some technical problems. Well, I would like to. I was trying to make a question, but I think my questions will be very similar to the one that Roger was doing, because exactly here my concern was you have. So you have an algorithm that runs so fast that you can get the solution in seconds. So in such a way that you can think, okay, why not going to make let's say something a little bit more complicated and to see what happens. And for instance, so I'm not going into these details as Roger was doing, but what can imagine is just do something close to what would be brute force. So if you have a system with just around hundreds of nodes, probably it's not so involved to get an exact result, to get an exact optimum. And then the point is to know exactly how reaching this global optimum, how it scales with the size of the system in such a way that we do it, for instance, when you make a partition into communities in a network, or problems like this. So make a small problem, try to get how it scales, and then to compare it with your approximate solution, and then also to see how your solution scales, and then looking to the improvements in this direction. So how you can approach this global maximum in some smart way that you can. So I think that this could be.
Yeah, no, I mean, from a scientific point of view, it's a very interesting question. And probably, I mean, we are sort of maybe playing in another people arena. Maybe people from operational research come and say, this is totally solved, 40 years ago, which probably is the case. Our point of view was more practical here. We have 141 trusts. Probably brute force, I don't know. I mean, consider that you need to, so some hospitals can move up to, I mean, the capacity of each hospital goes from 0 to 200 beds. Okay, so you would need to consider, looping for each of the nodes, different neighbors between 0 and up to 200. So it's a lot of runs, but maybe it could not be done by brute force. But I mean, in my experience playing around with this thing, random search optimization, it gave a pretty good solution. Maybe not the optimal, but yeah, pretty good. So for what we thought matters, it was good enough. But definitely, scientifically, it's important, interesting question.
Yeah, but then the point is that how you convince the politicians on helping, on making these decisions. I agree with you that you need to provide them with some simple tools that they can just check what is in their hands, and to see practically how they can improve and how they can play with the different parameters on this system. Okay, thank you very much. Thank you very much for the talk.
Thank you.
Lucas, I have also not a question but a clarification. On 3 maps of Spain. In the one in the middle, you have Madrid in red, Castilla-La Mancha in white, and Andalusia in green. Madrid is not able to transfer any patient to any community because it has no green neighbors, right? But the algorithm can be modified in order that Castilla-La Mancha is very close to. It's not at the critical, and it's not at the point. But if you are very close, you should also start to transfer patients.
Yeah. That would be an improvement of the algorithm. Yes. Or for instance, make it like 2 or 3 step Markovian. No, consider situations where you can. Right now, we are only looking. The state right now and the state of the others right now, but you can try to build to move according to what will. I mean, I move there because then another guy moves here. These kind of 2-step approaches could also improve further. And what we can see that in exactly the map you say, right? I mean, if Castilla-La Mancha moves people to Extremadura, then people from Madrid can be moved to Castilla-La Mancha, no? Or with the 2-step approach. So yeah, plenty of room to improve on these things. And again, probably operational research people will be able to do this, very, very like optimally, right? I mean, these are the people that should be doing these kind of things. But basically, we just did it because we wanted to help.
I have another question. How many steps do you need to find a solution, more or less, on average, or something?
Yeah, we weren't very systematic about that. We ran 100,000 realizations only because it was so fast. If I remember correctly, after 1,000 iterations, so after 1,000 realizations, the global Like the approximation to the global optimum did not improve much.
But in order, for each realization, in order to reach the minimum, do you have an idea of how many steps do you need?
What do you mean to reach the minimum?
Because you start to move patients, okay?
Mm-hmm.
You move patient and then you iterate and move patient until you get a minimum, right?
No. It's just one step.
That's one step.
Yeah. So you have maybe 10 patients that you cannot give any care. So you need to send them somewhere. And you look around and then you say, okay, I'm gonna send it to this hospital, and you send them. And you do that for all the nodes. Okay. So if you have a situation where you can send patients to 2 hospitals, then you have to select one, and you do this selection at random, and you do all these things at random. And then once you do that for all the hospitals, you look how many, for instance, if you do that sequentially, you look at how many people you could move, and that's the outcome for one realization. And then you repeat it again by choosing randomly another set of options.
Then avalanches are not possible in your model.
No, there's no self-organized criticality here.
So there is no way that you transfer to a hospital and that hospital becomes overwhelmed as well, and then you start to transfer and move people around.
Well, you could. That's in. If you remember at the beginning, we said you can use. Okay, let's go back quickly here. You can do sequentially or in parallel. Okay, in parallel is what you say. In parallel means that all the nodes do the load balancing at the same time, and by doing that you can overwhelm a receptor, right? If a receptor is overwhelmed, then he in turn will need to load balance, and then it can happen what you're suggesting. Most of the analyses have been done with the sequential, just because from an ethical point of view, we cannot accept that a receptor will be overwhelmed, right?
Okay, thanks. I'm going to abuse my condition of moderator and make the last question. You are preparing the operational version of do you think the operational version of the model will be ready for this pandemic?
Okay, so I have to be very clear. This model was ready in April. Ready in the sense that the very basic solution was ready. If we know the demand of each hospital in a region, and we know the capacity, and we know the distance between hospitals, so the position of each hospital, we can calculate what would be the optimal way of load sharing. Of course, it has all the caveats, right? Then, like Montserrat said before, maybe some of these patients cannot be moved because they are very ill, or some other considerations. But to give this kind of policy or this kind of advice, we could already be giving that in April. And actually, that was what we tried to do with the Comunidad de Madrid, but we were unsuccessful. Now, what we're doing now by building this front end is to make things simpler for the policymakers. No, if they have a software which is it's not running Fortran and it has a very sort of nice front end that you don't really need to touch the code or anything, then the adoption of the technology will be easier. And we hope to have something ready in, I don't know, in a few weeks. But again, if we are not applying this right now, it's not because it's not yet ready. It's because it's difficult for scientists to give. It's difficult that policymakers will adopt a new technology that comes just from from a bunch of scientists, I would say. It needs a longer learning curve to adopt the technology. That's my experience, at least. I can't hear you. I can hear you, Álvaro.
Sorry. So you are not very optimistic that your method or your algorithm is going to apply right now, or because in the next weeks you are going to need it very much in the UK probably, and also in Spain and other countries.
Yes, definitely. Right now we could be load balancing already. As I said before, back in April, we didn't need it because we had Nightingale hospitals, and those were enough to be able to escape from hospitals being overwhelmed. But right now, in this new wave, in the January wave, doesn't seem so likely that Nightingales will be enough. So yeah, it would be great to use this, and we have tried. I mean, we have tried, you know, to speak with the relevant people, but it's a whole machinery which is very difficult to move in a certain direction. That's my experience. I'm not super optimistic. I mean, it would be great, and we would be really happy to, you know, to offer this approach and work with the policymakers. But yeah, in my experience since April, the feedback I got is not very encouraging.
So the summary is that if they need you, if they ask you for help, you are ready to help you. But if they don't ask you, you cannot do anything, right?
Well, I mean, yeah, that's pretty much it. I mean, if we are seeing over Twitter, right, a lot of people that want to help from the scientific community, and they are not listened, right? It's not only on the case of load balancing, but on many other fronts. So it's difficult. The scientific culture is, I mean, the transfer of the quick and efficient transfer of knowledge between academia and in this case policymakers is not it's not optimal, and it's something that I guess hopefully will change, but yeah, it takes time, I guess. I don't know what to say. A lot of politics.
Okay. Thank you very much, Lucas. It has been a pleasure and a privilege to have you here. Do you want to say something?
Who, myself? Thank you very much for inviting me. It was great. And I mean, I'm very happy that you guys are running this sort of colloquia on complex systems and COVID. I think we have a lot of things to say on this matter. So thanks, guys.
Thank you.
Thank you.
Okay.
So I think
just to remember that this is the last talk of the series.
Yeah. Okay.
So we don't.
I just want to say this, that Alvaro, we missed what you were saying at the end. So that we are. So we have this last talk of this second leg of this seminar. So we hope that we can do something again in the future. So we will make a decision for the different boards. So how to continue. But in any case, we think that it's a way to put in, as you were saying. So what we do it's very important to say that what we do in this complex systems community, that it can has a clear application in this case to this very serious problem that we are facing as a society, as is this COVID pandemics. And it's important I guess for our community to say that we have something to say, and that the pity is that we are not used, the politicians who really listen to us, and but it's a very tough work to be done in the next future. But we think that it really deserves to make such effort. So I just want to thank all the speakers that we have had, and in particular thank Lucas, that you know that you are always welcome to this Catalan community. You can feel at home with us, and so we hope that okay, to see you around soon, and perhaps sharing all these ideas in some of our periodic meetings. So real meeting people, not like these things that we are doing right now. So thank you very much, Lucas. Thank you very much to all the audience, and just looking forward to see you around for some time in the future. Thank you very much.
Thank you very much, guys. Bye bye.
Thank you, Lucas.
Thank you.
Thank you.
Thank you, Lucas. Bye-bye.
Thanks, Jordi. Bye.
Good luck with the pandemic.
Thank you. We're gonna need it, all of us.
Okay, yeah, for sure.
Sure.